with many triangles. Go ahead.
Okay, thanks to the organizers for the opportunity to talk here. And as Shobit said, I'll talk about sparse random graphs for a change and with many triangles. So what they mean and what I will talk about will be clear. But let me first tell that when motivating the problem, I'll probably go over a few things for the diverse audience, so that which will be somewhat basic to some of you, but for some of you, hopefully it will explain a few things which will help understand the results and the context. Okay, so we will consider the simple random graphs, the Ardashani random graph, where each edge is present with probability p, and all our graphs are simple, undirected loopless graph on n vertices. N will always denote the number of vertices, no multiple edges. And each edge is present with probability lambda over n independently of each other. So the simplest setting possible. And some very well-known facts to probably all of you. So is that the number of edges is linear and is approximately this quantity. By linear, I mean linear in n. And then on an average, the graph looks like a tree. What I mean by on an average, you pick an uniformly random vertex. See, it's our neighborhood. It looks like a tree with high probability. And it contains a small number of triangles, only a Poisson that depends on the lambda itself. So no n there. So these are the properties of this graph, which is somewhat well understood by now. And then these are mathematical properties, right? And then some practical facts, that we see graphs in real life that are sparse, in the sense that have n linear number of vertices and linear number of edges in them, and typically linear number of triangles in them. So, and not only that, so it's not only that the number of triangles are large, the number of vertices that are part of some triangle is also large. It's not like only a few vertices contain the large number of triangles and the rest of the graph is like a tree. It's not like that. So they are kind of spread around. So these are not mathematical facts. These are observed facts. So it is probably safe to say that these facts are not mathematically understood. So so this suggests that the networks that are frequently observed in real life are mathematically rare. So the question is, can we still devise a mathematical model to understand this phenomena and to generally understand this phenomena? So now I will go into a very specific model and tell you what that model does, and then we'll try to formulate concrete questions. Okay, so consider this model on space of all simple graphs on n nodes. So it's a probability measure on all such graphs, which puts mass proportional to this quantity, exponential an, which is a number that is bigger than 0, depends on n, possibly depends on n. Beta is a constant, again, assume bigger than 0. And fg is some function of the graph. So to understand this measure, what it does, when beta equal to 0, it's just uniform measure on all graphs. When beta bigger than 0, it favors the configuration when f of g is higher, right? So this measure will favor the configuration. So if you think of f as the number of triangle, then this measure will favor the configuration where there are more triangles. So one would expect, or one would think, that this will do the job. And why one considered this? Why not a polynomial, say? So these are called exponential random graph models. I have not invented this. These are known in the literature for a while. So, and so a very vague explanation why these models are considered by statisticians. So suppose we know the normalizing constant, how to normalize it, suppose. So, and then someone tell you with a magic that what that normalizing constant is, and that the normalizing constant is differentiable with respect to beta, then you can take a derivative and see that you can compute the moments of this fg when, say, if it was a number of triangles, and you can compute them in exactly in terms of this derivative of this function and z and beta. So, but then we don't have a magic wand. So, but hopefully this clarifies why one would like to think about these models, right? Okay, so now we will slowly go into concrete problems. So how rare are the networks that contain a large number of triangles? So here, always when I'm talking about networks or graphs, always I'm talking about sparse graphs. And how rare are the networks that contain a large number of vertices that are part of the triangle? So these two are different questions. So we'd like to understand the networks that has large number of triangles. We'd like to understand networks that have many vertices that are part of the triangle, right? And can we propose a suitable ERGM model to explain the discrepancy that is observed between real-life networks and mathematical networks? And we don't have a magic wand, so can we do at least some tricks to get normalizing constant of such model if we can propose one? So these are sort of the questions that we'll be considering. Questions, comments?
What is large?
Yeah, so by large means growing with n, but typically we'll think about linear number of triangles, but our results go beyond linear, both more and less. Yeah. Other questions? Then a formulation. So can we prove a sharp upper and lower bounds of, okay, there should be a log of this quantity, that probability, T is the number of triangles in order training graph G and P, where P is lambda over n. Can we prove sharp upper and lower bounds of this quantity? And that's the first question. And the second question is, suppose we can prove one, then can we say what is really creating those triangles? Like there could be many ways to put triangles in a graph. So what is responsible for creation of large number of triangles? So suppose Kn is n, some constant times n. And we know that in order training graph, this probability is very small when it's sparse. So when you put a large Kn there, can we explain this event? So these two are concrete questions that we are going to now investigate. Questions, comments? Okay. And then some more explanation about why isn't it a classical LDT problem. You use Verdon's hammer, compute exponential moments, and try to get something like this. So I guess this was explained a bit yesterday as well. So so how we do usually prove and bound on the, and this is very simple for probability. So an upper tail of a IID sum, just exponentiate the sum, assume that moment generating function exists, and write like this, use the independence here, and like within a few lines you get this. I don't want to like spend too much time here. So, but here that the fact that this was sum of IID random variable helped. We can write the number of triangles times 6 as a sum as well. But there are peculiar dependence among the terms, which prohibits us from using this sort of arguments. And then what is the state of the art? So we are not the first one seeing this problem. So in last 1 decade or 2 decades, the problem got, I think, problem has been investigated for 20-25 years, and last decade has seen enormous improvement. So but all in the range, this range, when P is between log n over n and 1. So the problem, so usually the upper and lower bound that were obtained using the classical concentration inequalities were summarized in this paper, the infamous upper tail of triangle. Let's get some more. Sorry. And so when P is independent of n, that is the dense setting, then this problem was solved by Chatterjee and Verdon. Then the variational problem was solved by Lubetsky and Zhao. So, and then when trying to solve this problem, the theory of nonlinear large deviation started in. So this was also a nonlinear large deviation. This started the study of this sort of quantities when P is sparse, and it has a range which the P was in the not in the dense range, but P was like an inverse, so 1 over n to the power 1 over 42 or something. So if I remember correctly. So up to there, you could push the P, but not beyond that. And so it got further developed. So when I say further developed, in one of this, so in this paper, the range of P got slightly smaller. And in this paper, actually a different problem, eigenvalue problem was studied. So, but all in sparse settings. So finally, this problem got settled in this whole range by this paper by Harel, Muset, and Samotej. And the related variational problem was solved in this Lubezki-Zhao, again in this paper. So here they express the problem in terms of a variational problem. They solved it here as well, but the problem was solved before in this paper, the variational problem. Okay. And all of this, if you note the range of this P, they do not consider the range where P is a constant over n. They're all sort of somewhat not so sparse, not so dense switching. Questions, comments? Okay, so now let us go into our first main result and a rough statement sort of. So when P is lambda over n and Kn is going to infinity faster than log n cube, I'll comment more on that later, and a constant a bigger than 0, which is independent of n, then we can show that this thing happens, that log of probability, the number of triangles bigger than or equal to Kn is approximately this quantity. So by looking at it, anyone wants to guess like what would be the cheapest way to get this probability, or what would be the cheapest way to construct this many triangles in the random graph? For the question is for those who already don't know the answer. Okay, I guess everyone knew the answer. So this is basically just planting a clique of appropriate size. And when you plant the clique of appropriate size, you get a lower bound immediately. And the lower bound is this. And this lower bound matches this quantity, and there is no more fancy math. So this is the lower bound. So all the works go into the upper bound. Again, sorry. Okay. So the upper bound is difficult. So this is the cheapest way. Indeed, this is the cheapest way to create the appropriate number of triangles. And for the upper bound, we basically modified the arguments by Harel, Muset, and Samotej. And we got this result that when Kn is bigger than and growing faster than log n cube, then this quantity is equal to this when epsilon n is the error term, and we have some degree of handle on the some degree of handle on the error term as well, but that is not that is far from optimal. But we do have some handle on the error term. And then when you have this quantity, the next question is, okay, so you have proved using the unsearch that there is a clique somewhere, and that the unsearch and some more mathematics gave you that this is indeed the correct way. But then what is, or how does the graph look like when it has so many triangles? So we have some handle on that as well. So I'm giving you a rough statement because making them precise means I introduce more notations. So all triangles, so what we can prove that when a graph contains a large number of cliques, then a large number of triangles, there is an appropriate size clique. So all of them are contained in a clique, but we could not show, or we do not know whether it's actually a clique, but what we could show, this is an almost clique. So what we mean by almost clique is a very dense subgraph, but as I mean, many people in combinatorics know that a very dense subgraph might not contain a very large clique. So, but what we could show that conditional on there are many triangles, there is a very dense subgraph, what we call almost clique. But unfortunately, this is the disappointing result. That so basically everything is in a very small part of the graph, and you can throw it away, and then the graph is exactly the same as the Arter-Freini graph. So the local limit does not change. It remains unaffected even after conditioning by such a rare event that there are so many triangles. So what we believe is nice math and still disappointing. So some new developments. So as I said that I'll comment on that log and cube. So after a couple of months after our results, so the upper tail, so we were mostly interested in Kn when Kn was linear, but other people were interested in the whole upper tail. So they proved that our result holds as long as this condition holds. This means that Kn has to be bigger than log n cube over log n. So our result is from log n cube, but they stop at n to the power 1/10 over log n. So in this region, our result holds, the similar answers hold. And when this does not hold, then basically they showed that the triangles are basically vertex disjoint. So the Poisson approximation holds. So these are two regimes, and these two regimes completely described. So this is the quote from their paper: the two results together settle the long-standing upper tail problem for the number of triangles in the case where the average degree is constant. So any questions on this? You want me to elaborate?
Do both these papers also consider the regime where t is between constant over n to log n over n? The degree is not constant.
No. That's a very good question. So that is considered in the paper, I think, in the paper by Harold Muset and Samotij, and then another follow-up paper by that paper definitely had Harold in it, but there are other 2 or 3 co-authors that I forgot. Yeah, but that is somewhere considered. It's Poissonian in some cases, and for the again when it gets a very large number of triangles, then they cluster. But I forgot the exact. Okay. Yeah. Then again, it's nice to read a statement like this, but this is disappointing in some sense. So we get upper and lower bound on this, conditional on this. We know that we are dealing with the same Arter-Freini graph on an average, but we know that localization is happening. There is a peak somewhere that is taking care of everything. And the graph is not only tree-like, this is indistinguishable from Arter-Freini graph in the local weak sense. Okay, so this motivates that we need to look at somewhere else. So can we inherently disturb the local structure by constructing appropriate event? So this motivates this following question, that can we look at the number of vertices that are part of the triangle? So if you consider the number of vertices that are part of the triangle is say n over 3, then you already disturb the structure in the sense that you know that with probability 0.3, the graph is not tree-like. So forget about Arter-Freini graph. The graph is not even tree-like whenever you condition on the fact that number of vertices that are part of triangle is linear. So, but in sparse random graph, only a small number of vertices are part of the triangle. And if you condition on some event, then you know that it will not be tree-like. Then the question is, can we study this event as well? Okay, so we can write this number of vertices that are part of the triangle like this. And we could hope to, the first starting point would be to use existing machinery. So one could try to use the Chatterjee and Dembo's nonlinear large deviations smoothness condition, but we could not check it on a polynomial like this. So this is cumbersome. And then the second way would be to try using Harold Muset Samotij type argument, but that is a very different argument. They basically focus on denser and denser graphs and try to throw away depending on, so they try to increase the vertices a bit and the edges in another way, but in such a way that the graph remains dense. But this is not the answer that we'll look at. So we want to maximize the number of vertices that are part of the triangle. We have to think about it in some combinatorial way. And some new machineries has to be built.
Sorry, just a very quick question.
Yes.
I mean, previously when we consider triangles, we always consider the multiplicity. Here, why is that the formula doesn't have?
So this formula does not have a multiplicity, so there is no multiplicity. Yeah.
So you
This-
don't need.
It's not that we don't need, it is not there. Yeah.
So just as, maybe I'm being your straight man here, but just as the cheapest way to have a lot of triangles is to make a clique, the cheapest way, it seems, to have many vertices as part of a triangle is to have a bunch of vertex disjoint triangles.
Excellent. That was my question in the next slide. Yes.
Oh, okay, sorry.
Yeah.
But that's a little confusing as well. I guess the original motivation, if it's to make things look more like real networks,
Right.
well, then forcing the triangles to be vertex, creating a pressure for the triangles to not share any vertices seems strange in some ways.
True.
I mean,
We agree with you, and that is why we were discussing me, Remco, Frank, and Mark last week and last couple of weeks. Like, is there a better way to do this, better model to come up with? We don't have any. So we are trying to see how far you can push the exponential random graph in this case. And but as I said in the beginning, like, I mean, I think it's safe to say that we don't understand how the triangles get created in social networks. So yes.
So have you tried looking at random intersection graphs?
So yes, that is another thing again that we were discussing last time. So they are in the limit. In the limit, they are basically again tree-like, so random intersection graph. So it gets created like this, and so there is these are the vertices and these are auxiliary vertices. And you saw one of this element, wherever there are edges, you create a clique. Wherever there are edges, you create a clique. And in the limit, how it behaves is like a tree again, but a clique tree. So they just have an intersection of one vertices. So which is again not what we usually see in, say, real world network or yeah. Random intersection graph has that problem, and then the random geometry graph, where basically the sufficient statistics is the whole graph. So n vertices, n data points, and n size sufficient statistics, which is probably not again yes.
So the epidemiologists like what they call household models, or maybe I think you guys call it random motif models or something like that, where I just create sort of a distribution of small clicks with external stubs and then match the external stubs like in the configuration models, and you will sort of a configuration model on clicks, on top of clicks. Or if you want, take a configuration model and randomly replace the vertices by clicks. So in your example, take the Erdős-Rényi graph, and whenever you have a degree 3 graph, replace it by a triangle. That would be probably the simplest version. So every degree 3 vertex becomes a triangle, otherwise you leave the graph as it is.
And what I do with a degree 5 vertex?
You leave them. I just came up with some way.
I see. So we were considering another, I mean, that we can discuss offline, another model that Mark proposed. This might work. So the problem we have to always keep in mind that we need distinguishability at some level if you want to come back from data to the model. So going from model to the data is one business, and coming back from the data to the model is another. So we need to preserve distinguishability. I'm not sure. Maybe it is.
What is your definition of distinguishability?
So that you do. Okay. So you need to. Okay, you need to estimate the graph parameters, right? What from where you are creating the. I
only have one parameter, p. You build an Erdős-Rényi random graph, and now every degree 3 vertex you replace by a triangle.
Maybe could work. That we'll have to throw triangle. Yeah, that could be one explanation. But yeah, we'll have to think more. Good questions. Other questions, comments? Okay. So if not, then was this my next slide? Yes. So again, this was our second main result, that roughly it tells that when kn is growing fast enough, faster than log n, then log of this quantity is approximately this. So if you don't want to read it, just don't read it. So this is the result. So, and again, as answered, what is the idea here? And the idea is that the triangles are vertex disjoint. So you create vertex disjoint triangles, and they are the cheapest way to get the lower bound, but the upper bound is harder. So for this, we have to come with a decomposition lemma, which is completely combinatorial. To basically, we need some sort of compactness when we do this. So we need to throw away the bad graphs. So how do we throw away the bad graphs? Is through that decomposition lemma. But I'll come to the decomposition lemma if time permits and interest is there. Okay. So yeah, I more or less explained what I wrote here. So the calculating this lower bound is easy. You just sit down, you can compute it. And the upper bound is via the decomposition lemma. So let me just go briefly into it. So okay. So no random graph here. So suppose the number of vertices that are part of the triangle of a graph G on n vertices is k, right? And then make it basic. So what I mean by basic, delete all edges that are not contributing to this event. So if deleting an edge is not disturbing this event, delete that edge. That is the basic graph. So you've got G basic. And the decomposition is the following. First, in a greedy manner, take out all the vertex disjoint triangles. And when you are done with them, at some point you won't find any more vertex disjoint triangle. Then start taking out vertex disjoint edges, and they have a very particular structure. That is, they will form a triangle with the first layer, all of them, and so on. And there is a third layer, which is an independent set. And there are two things that can happen. Either this will form a triangle with an edge in the first layer, or they'll form a triangle with an edge that is going between first and second layer, right? And suppose there are L1 vertices in the first layer, L2 vertices in the second layer, and L3 vertices in the third layer, then you kind of get a counting lemma of how many graphs are possible that are basic. And I hold on the number of their edges. So with that counting lemma, there is an expression, so that there I won't go, there is an ugly expression that you get. And if you optimize over L1, L2, and L3, then you see that L1, the optimal is L1 contains almost all the vertices in triangle. So this is the basic rough idea of the proof. And this lemma might be of independent interest because this does not involve any probability or large deviation machinery, rather just a decomposition of a graph. Questions, comments? Good. Okay. So now, as we started discussing that we'll come up with some sort of exponential random graph model. So trying to maximize the number of triangles is affecting only a tiny part of the graph. So we saw that it's ineffective, although it was long-standing open problem, but it's not solving the real problem. And maximize the number of vertices in triangle appears to be a better idea, although may not be a realistic better idea, but in terms of a model, it can give us something. So this motivates the following ERGM. I guess you all could guess what I'm going to propose, that we tilt, so PG is the probability measure of the sparse Arter-Feini graph, and we tilt it by this quantity exponential beta times log n times vertices that are part of the triangle, right? And I guess, yeah, we are familiar with what it intuitively means. Any questions on the model?
So remind us why beta log n?
Good question, very good question. So this is essentially n log n, right? So when kn is n, This is n log n. And when we are proposing this model, actually, this is fraction of vertices that are part of the triangle, and this is n log n. That is why it is log n. So this is the correct scaling.
Sorry, it's log n with parentheses around it.
Yes, log n is a quantity. Here is a parenthesis. Yeah. Yeah. Not VTG is not with inside the log. Yeah. So model is clear, right? Okay. So we're considering this, and we can, as we said, that we don't have a normalizing constant, but the trick was to use that large deviation result that we showed and get this normalizing constant using that large deviation. That the normalizing constant has an approximation, which is like this. And we have a phase transition as well. When beta is, I mean, probably some of you can see almost looking at the result that when beta is less than 1/3, the fraction of vertices that are part of the triangle converges to 0. When beta bigger than 1/3, the fraction of vertices that are part of the triangle converges to 1.
Yes. So maybe you should take beta equal to 1/3 plus theta over n or something.
Next slide.
Oh, sorry.
Coming there. So excellent. So okay. So forthcoming result. So we just saw that beta when it is away from 1/3, this is not a good model. So we can take beta equal to 1/3 plus theta over log n, which is the correct scaling. And then we could show that this converges to a quantity that is strictly between 0, 1. And as far as we know, this is the first exponential, rigorous studied exponential random graph model, which creates a linear number of triangle, and it is sparse. But as it has anomaly, I'm not saying that this is the best model, but this is still a model that creates, that has non-trivial structures. Okay, and what is, or what are the machineries for, yes. So what are the machineries for this? So the decomposition lemma, we are saying it is not, I mean, in terms of the error, it is not as bad as the structural lemmas that we have in dense cases. So we could make it even finer by going a 4-level decomposition and prove a result like this, where the second order is also correct. So when we have that, we could prove such a result. So yeah, this is more technical, but this goes in the same line by incorporating another levels in terms of whether this vertex is connected to two sides of one edge in the first layer, or the one vertex is connected to this layer. So we have, if we decompose in 4 parts, then we get an exact control up to the second order.
So you mentioned before that there's not that many of the second layer. So most triangles are vertex disjoint.
Most triangles are vertex disjoint. That result is not there in our that paper, but in this paper that will be there. Yeah. Yeah. But you see, I mean, here, so once we have something of smaller order than the first term, we could prove that most triangles are vertex disjoint, but it is not, I mean, we are not required to prove a finite decomposition lemma to get that result. So the finite decomposition lemma only give you how good that approximation is.
As a triangle, but they will not be far from each other.
I did not.
Is a local weak limit just sort of?
It is definitely not a tree. Whether it is very different from Ardashirani or not, that's a debatable question. So, but even the support is different. The supports are completely disjoint. So Ardashirani graphs, local weak limit is completely supported on trees. And
right. Here you have some, I mean, with some probability of utilizing the triangle. So
right.
But we don't, do we know the local weak limit exists?
No, that is, yeah, and we are not sure whether we'll be able to prove that, but that was the main thing that we're targeting, but we are not there yet.
Question, because due to Christian's inspiration, Wouldn't it be then the local limit looks like a tree, but blown up majority of the vertices have this blown up triangle type thing? I'm just wondering, because what Christian said is kind of usual delta y delta type of transformation in combinatorics. Usually the degree 3 vertices, it's kind of y. You can always transpose into the delta, which is a triangle.
So we have some guesses.
Or if you have a larger degree vertices, you can always take two pairs of those and put additional edge. By doing so, you do not touch the edge density at all. The degree 4 vertices, I pair them to 2, and then I put the additional edges between them in kind of subdivision, and then you add an edge. But by doing this, you don't touch indeed the overall edge density, but then you increase the number of triangles. Of course, they kiss at a common vertex, of course. So
could be that is, but we have another. I mean, I don't want to say it because we are not sure whether we'll be able to prove it or not. So we have the guess that you have the vertex with some probabilities in a triangle. So if it is a triangle vertex, it will have additional some number of edges, which will come from the Poisson distribution. And the other vertices that is not in a triangle, that will have another Poisson number of children. And those children with some probability are triangle vertex or non-triangle vertex.
Kind of a type
Yeah.
process, some of which has this triangular.
Triangles kissing.
Triangle kissing.
They will not kiss.
Yeah, triangles are disjoint.
But there is a multi-type version process where you look up this transition property.
So that's what we're guessing.
Yeah.
Proving it's a
How
different.
about you say there are no kissing triangles?
That we know.
Okay, so I guess more or less time to summarize. Oh, before I put this slide here, because some acknowledgements are needed about the ERGM literature. So the primary use of these models are in this paper by Holland and Leiden, Frank and Strauss. There are many more sufficient statistics that get developed in these papers, and there are hundreds, if not thousands, other papers where they come up with new sufficient statistics. And the first two theoretical results on the dense regime are by Vamidi, Bressler, and Sly, and then Chatterjee and Diaconis. And again, there are more results on dense regime by many authors. And in the sparse regime, the only results that we know of are by Mukherjee, but that's on the graph that are tree-like. So you can consider, for example, Q star, R star, or combination of them. And there you use a contraction principle on a result by Bordonave and Caputo, where basically they consider large deviation of neighborhood distribution of Ardashani graph. So, but these results run on a different scale than our results. So you cannot derive our result from Bordonave and Caputo. Okay, I'm almost done. So, So we had to develop newer machineries. Yeah. So this is the conclusion that our proposed model produces graphs that are not locally tree-like, and they're still sparse. They have still some anomalies. Okay, summary. We proved this result, and we showed that this is not, mathematically nice, but for our purpose, kind of useless. And we proved this result, and the answer is that this at least gives the triangles are spread out somewhere, and a new ERGM models with some intriguing properties. Okay, and some open questions. So conditionally on the triangles bigger than or equal to Kn, can we prove final results? So this, I believe, is a hard question. So we proved that it is a almost clique. So a graph on, say, k vertices. So forget about our result. A graph on k vertices, but or n vertices with say n vertices with 1 minus 1 over log n times n choose 2 edges. So n vertices and this many edges, but they are also, if you consider the extremal Turan graphs, they have a very small clique. So it doesn't say that it is a clique, it just says it's a very dense subgraph. So can we prove final structural results like it is indeed a clique or something similar. We don't know what to force. Maybe forcing independent sets to be smaller, but then the arguments, we know that it gets very hard. Maybe quasi-randomness, I don't know how to use it. So yeah, this is probably a hard question. And so conditionally on this, can we determine the local weak limit of the graph? As we said that we have some guesses and some advances, but we don't know what is the limit. So, or is there a simple argument to show that the limit exists? That would be nice, because then we can show that, okay, it exists, and we know that it is not tree-like just by trivial arguments. So, so these are another set of questions. And what about extending the results to other subgraphs? So for our vertices in triangles result, we believe that for cliques, the decomposition lemma extends easily. The calculation becomes harder, but the lemma extends easily. So hopefully for cliques, this will be easy, but for other subgraphs, we are not sure. Yeah, other than that, questions?
What about the giant component?
What about the phase transition for a giant component?
So if you have the local weak limit.
No. Yes, I'm aware of that. But what if you didn't have so? I mean, do you first need to solve the local weak limit?
No, of course not. Of course not. But so maybe the exploration process directly.
But wouldn't that more or less give you the local weak limit?
Yes, but so if we are not interested on the size, just that order n component.
Oh, just the transition point.
Just the transition point.
Yes.
Where there is an order n component, then maybe we could use instead. So sometimes it will go down by 1, or sometimes it will go down by 2. So maybe, I'm not saying that it is easy, but maybe. Yeah, only the giant component. Yeah.
I guess this is a related question, but I'm not that familiar with ERGMs, so maybe this is obvious, but when you, is the total number of edges roughly the same as the Erdős-Renyi graph without the triangle term? Or in other words, do the triangles get formed by stealing edges, as it were, from the rest of the graph, or does it get those additional edges in the typical case without having to pay for them? Obviously, in the latter case, then you would know where the transition for the giant component is, and in the former case, I don't know.
Even yeah. So when the vertices in triangle case, like they are formed pretty deterministically, like there is a dependent structure on them, right? So when 2 gets created, the another gets created. So it's not like you add the edges independently somewhere. So if you put them independently, then it will be easy to.
But we do know that if you throw away all the triangles, the number of edges is going to be the same as what it was originally. Love that I know.
So
basically the triangles are added. Right.
So the typical number of edges is the number of edges in the base graph, the Erdős-Renyi graph, plus 3 times.
But still doesn't quite. It doesn't tell you exactly what the transition will be, right? Because the triangles will make it spread more thickly. The transition point will likely change.
When you reach a triangle, then you get all of the other neighbors of all 3 corners of that triangle. So that.
So it must.
That makes it sound like the transition should be around 1/3, or for.
I think it's going to depend on the number of triangles you have as well. So it's going to be
Right, the probability that it is a triangle. Okay, yes, the same kind of branching process that Ian was talking about.
It's a 2-type branching process, so it should be survived.
So you said several times about realistic graphs. So is there a benchmark for that? I mean, is there a data set or a graph which is
so basically
realistic?
Mark sent me some data set last week. I was analyzing them, but yeah, like so per vertex, if you look at per edges. So if you look at per edges number of triangles, they are sometimes, I mean, they behave pretty differently. Like sometimes per edges, whenever one edge has, okay, let me explain. So for some graphs, you have one edge and there are a huge number of triangles incident to it. But for some graphs, it is not the case. So there was so there were two networks at one of which looked like this and one of which looked like this. So the triangles are spread more, and in one the triangles are really coming from small clusters. So it depends like which networks you see, but yeah, I could not decipher like other properties, like what to use there or what models would be appropriate there. Yeah, but just did some basic analysis and came up with this.
So this is not exactly your statistic, but just as a, I guess, a proposal for something slightly different, which has been proposed in the social science literature, maybe even some of the references that you...
K triangles, the alternating K triangles?
Okay, alternating K triangles, sure, yes.
Yeah.
Anything to do where you characterize, let's say, I look at the number of pairs of vertices with degree Z, with co-degree 0, with co-degree 1, co-degree 2, encode this as a distribution or a vector, and then and there are some specific suggestions which we can discuss after the talk.
Yeah.
That empirically that seems to do well as per the literature.
Yes, yes. So that is a very good point. So I have been thinking about this a bit, but I don't know how to prove large deviation results unless you have a good answer. Like, so if you have a guess about what the event which will create the cheapest thing, then the proofs are not easy but doable. But if you don't have, so suppose in the dense regime, so when you know what something looks like random, you know what we are talking about, it's quasi-random. So but here what we mean by the triangles are spread over. So is there a notion of that?
Instead of thinking your lower bound argument the way you are thinking about it, maybe one can again go back to Bourdainov and Caputo and think about, this is a two neighbor. This feature that I just described only depends on the two neighborhood of the graph. So, but anyway,
yes, but whenever cycles appear in large numbers, Bourdainov and Caputo is out of the window because that in that scale you don't see any cycle. In that scale you see trees.
Yeah, you'll never see that many cycles.
Yeah.
That's to look at n log n scale.
N log n.
Right. So you'll never get that. I see. But we should talk more.
Yeah, of course.
I mean, this is maybe rephrasing Shurab's question. What kind of graph are you actually looking for? Because the one at the beginning, you weren't happy because they were like, it's like one clique. Then Shurav suggested one, you weren't happy about the random intersection. Christian suggested another one, you weren't happy about that one either. What is it you're actually looking for?
I wish I could answer. So yeah, it's not, I mean, yeah, if we have a very clear metric, I guess, when we can say that we are exactly looking for this graph, then probably the answer will be there somewhere. So,
what's the property that you're looking?
Well, the triangles are not all in cliques. Somehow if you look at somehow union or expressions of triangles, they're non-trivial, but they overlap. So you have edges that are in multiple triangles. I mean, this is the type of features that you see in social networks. And none of the models that we know so far actually produces this. So the random intersection graph is closed.
Does not have this behavior.
All the communities are cliques, and they touch generally in one point, but that's generally not what a social network looks like.
I thought that was a very good description. Okay. There are many triangles, and they don't just meet at a vertex; they meet at.
So it's somewhere in between these models that all of these models are much too extreme. So you're looking for something in between.
So this one still wouldn't work. Yep.
Can I comment something? There is something the there is kind of a three uniform hypergraph, but then there is a so-called high order connecting needs, which means that in case of the three uniform hypergraph, you can form an hyper edge as a triangle, but then you make connections only if two triangles share an edge together. So for me, it's like this three uniform hypergraph, not exactly three uniform hypergraph, because three uniform hypergraph, or simply shear complexes, where two-dimensional simple shear complexes which arise from something else, because you really insist that there are many overlaps along the edge, but not along the vertices. So in between, because it's kind of new to me, because I don't, I don't usually study something from real network. But if you look at the literature, sometimes they call like nested triangles or nested complexes, whatever in geometry, you know. Maybe you can inspire yourself from the properties, and then there are also concepts of the collapsibility. It's not has to do with the collapsibility, by the way,
Right.
but there might be some useful concepts from this discrete geometry because of the nature. The triangles are just two cells, you know.
Right.
Simple complexes. So, and it's a 0 cell, 1 cell, 2 cells, and I think you have a lot of these two cells sharing one particular cell.
So you're saying that vertices would be cliques and an edge between two cliques would tell you the size of the clique that they intersect on, for instance.
Like that. Yeah. Kind of rings a bell, but I cannot formulate it.
Okay.
And there'd be a degree, clique size, edge thickness
Sure.
distribution.
The cells have its own degrees, of course.
Thanks for the questions. And if there are more questions,
Yeah,
we can take
offline,
offline. So thanks, Suman, again.